let us start the recording also. So we are discussing on the CTVT sizing. So let us quickly check the syllabus also what we are following. So we are following for the module 1 that already we have discussed. Then module number 2, that is the equipment selection and sizing calculations. And in that module, the lightning as suggest already we have discussed. And after that, we are discussing other CT and VT selection parameters, sizing calculations, vendor drawing review and the comments. And in that, we are taking current transformer. And when it comes to current transformer sizing calculations, so we have discussed so far about the metering core sizing calculations, and we have seen that when we in switchyard or in subsystems we take the multi-core CT. So in multi-core CT, we take generally two type. One is the metering, and second is the protection. These two work we have from the CT. And this protections again we divide in for the two part that we mostly use. One is the P class protection CT, and next is the PS class protection CT or PX class protection CT we can say. So when we talk about the CT sizing, so we have to do this core sizing calculations. So the metering core selection parameters and the sizing calculations we have discussed, and the protection class core, their selection parameters and the sizing also we have discussed. And when it comes to PX class, so in the PX class the parameters is the same, but only addition point in the PX class core is that we have to specify the any point voltage and the CT secondary resistance and magnetizing current. And full load current is same as we discussed here. And we same will apply here the CT current ratio. So today agenda is the PX class CT and knee point voltage calculations. So we can start now. Should we start? I think everything is fine. So if fine, so we start. Are any query from the previous session? Today is very important discussions, very important class. So I need your active. Please be active on the chat box. That is the only request that I am doing, and rest I will take, but the one request that you have to do, that is active on the chat box, at least CCNC or CLR, whatever you feel fine, that is okay. Okay, so let us quickly so today agenda CT knee point voltage calculations. Let us quickly again revise, again refresh the all yeah, thank you Hari. So let us quickly again revive about the CT basics and the core basics. So refresh of CT basics. The current transformer have two jobs to do in the power system. Firstly, it step down, or we can say they scale down the current to such a level that can be easily handled by the meters and relays. And the standard secondary current rating of CT used in practice are 5 ampere and 1 ampere. This standard 1 or 5 ampere, actually this frees the meters and relay manufacturer from the actual value of primary current, so they can manufacture their meters and the relay considering 1 ampere and 5 ampere current. So no need to tackle that what is the primary ampere of current. So the manufacturer is free from the primary current value. They can take this one and they can design their equipment. Secondly, the CT isolate the meters and relay circuit from the high voltage of the EHV system. So we discuss again the CT basics to work here. So when it comes to for the calculations, so in the CT rating calculations we do the calculation for the each core, or we do the calculation core wise. So for metering core, I think these four parameters we have to specify, and as already we have discussed the current ratio. Yesterday we discussed current ratio of taking one solar project. Current ratio to be calculated based on the load, demand or the requirement. The accuracy class, these are the options available, and that can be selected as per the CT applications. Our system, the CT burden, to be calculated based on the CT secondary site connected instrument burden, such as ammeters burden, relay burden, or interconnected lead cable burden, and the ISF value 5. So these four parameters we need to specify for the metering core. And when it comes to the protection P class core, normal protection core, then again four parameters, the CT ratio. In place of the what is the change here we done in the metering code, it was zero point 0.2 or zero point 0.2, yes, only 0.2 percentage error. But in the protection class, we take generally 5P class, 5 percentage of the error. That up to this we can tolerate, because we are not doing any metering here. So if current is 5%, then there is no any major difference. The CT burden that to be calculated based on the CT secondary site instrument and the cable lead burden, and the accuracy limit factor ALF, that mostly we take 10 or 20. So the P class CT four parameters, I hope this is clear for everyone, and the metering core for these four parameters, this is clear for everyone, right? And that this two we have discussed so far in the previous sessions. Now when it comes to the PX class CT core, the CT ratio, same as we have discussed for the metering core and for the protection core, same concept apply to calculate the current ratio. So what is the change with respect to the P class core here we are doing? In the accuracy class to be selected as PX core, where is the accuracy class was the 5P. Here PX class, the CT knee point voltage as per the relay requirement we have to calculate. That is the one major difference, and that is the agenda for today's discussion. Magnetization current 20, 30 or 60 milliampere we generally we take. One parameters I can add here, that is the CT secondary winding resistance, and that called as RCT. This value also we can take. So this value we can take from the tender, or we can take from the manufacturer. There is some thumb rules that we can follow. So we'll come discuss on that, right? Yeah. So let us take today this PX class and start the discussions. And let us again take overall grid, and based on the overall grid, let us specify, let us distribute the, let us understand the CT core selection. So when it comes to the distribution, when it comes to distributions, so for in the distribution substation, for the distribution feeders, as you can see here, there is this distribution feeder for the commercial and the industrial users, this distribution feeder for the residential user. So for these feeders, what protection class generally we take, generally means as per the engineering practice, what protection class we need to consider here. Please active on the chat box, because again I'm trying to discuss the things in a detailed way, and if you not reply, then it will take time. So how I will do, I will cut the discussions, I will like minimize the discussion, okay, and I will go only point wise point as per myself as. So please be active on the chat box, that is the one request. I like, what is the class we should take, so we should take here, what is the CT class here, what should the CT class should be here, what should the CT class should be here, what should the CT class here, what should be the CT class here, for the protection purpose what we should take. Let us understand in the overall grid network. Can anyone unmute and they can explain? Please be like, can anyone unmute and explain what should be the CT class?
Depends. If it is if you are protecting the unit protection or a particular.
Let us start from the distribution and reach to the generation.
So even in distribution, if you are protecting, say, transformer or something, or a cable, you use PX class for that particular equipment. But if it is a overcurrent and earth fault, you can use a 5P10, that kind of class.
Yeah, 5P10 or 5P20 we can take. Okay,
Exactly.
let us take the snip and let us specify the class here. Okay, so this is my distribution substation, as we can see here, distribution substation, as we can see here, and from that we are distributing the power to the end users, right now. If please anyone can unmute and they can say yes or no. Anything, at least no, you can say it, not yes.
Yeah.
Am I correct? This is the
Yes.
distributions we are doing for the end users. So for uh, distribution feeders, we take two core city. Am I correct? Right now, in practice, if there is no any specifications, if there is no any data given to you as an engineer, what you will select? That only need to explain. Two core city
Yeah.
we take, right? Let us
Mhm.
take as per interview. Suppose you're sitting in the interview and you are going to say that I know the CTVT sizing and I'm asking you to specify the CT codes uh, in a grid. So how you will specify the CT codes for a grid? This two core CT, right?
Mhm.
Yesterday we discussed about the CT core selection.
Yeah.
Generally generally minimum one core for the metering purpose. Am I right?
Yep.
Second core for the overcurrent and earthfall protection purpose, right now.
Yep.
And that is the minimum requirement.
Exactly. So the thing is, like, according to the standards for the metering, we will need more accuracy. If it will be a, like, the class 0.2s for the metering.
Yeah, point 2
And
yes class, yes. And for the overcurrent and the fault,
I mean, 5P10.
yeah,
But
5P10,
but or
5P10
5P20 also.
or 5P20 also. Anyone we can take, anyone we can take. And generally 10 or 20, this two value mostly we consider. And we can go 5P20 also, right? There is no any issue. if if specifically are any special requirement of the client, they are asking for the px core in their tender specification, in that case we can select, that is not wrong. But yeah, 5p we should go, we should take here. We can take if there is only a special requirement provided by the client. Then if this is transformer here, so for the transformer protection, this incomer, this is outgoing from the trans. So what should be a city, how many cores should be here, and what should be the protection class, and how many city cores should be here, and what should be the protection class. Similarly, we need to specify, this is my again one grid substations. So how many city cores we should put here, how should many core cities we should put here, and what should be the protection class of that city. And when it comes to the generator, so here we have generating substations. So here what should be the city, like how many core and what should be the city protection class here, that we should know or we should specify right now. And this I wanted to discuss here, but I think you are only coming to listen me, not to exchange your information. So I'm not going to continue because it will take again 30 minutes, and I wanted to cover myself first.
Now, Raghav, this is something. I'm not from the substation background. This is something very important, to be honest, Raghav. If you can
But
guide.
actually what happens now, we require the feedback from the participant. If they are only sitting and listening me, so why I
No,
explore a lot of,
no,
because we
no.
cannot see, this is a 2 year syllabus that I cannot complete in 2 years also.
No, I totally understand. Totally understand.
If until unless you are not eager to learn and you are not quickly reply yes or no, then uh, time and energy both are limited.
No, sir, we are eagerly check your means we are taking sir your lecture, but you are depth knowledge. So we don't want to any excuse. So I learn from so that we don't any comment on that.
No, Raghav, just go ahead. Let's have a
Yes, sir.
discussion
Go
about
ahead,
this
sir.
one. Okay, say.
Your knowledge is depth, so we don't say anything about that, sir.
Okay,
Yes,
so I'm
sir.
leaving this and you do. Yesterday we have discussed on that. Okay, we have discussed yesterday about the city core selection, that for what voltage, how many core we should take. Yesterday we have discussed about this. Okay, I just wanted to apply those discussion in complete grid network. But anyway, yesterday we have discussed about the core selection. Yesterday we discussed about the type of the core. So take yesterday discussion and apply it for this grid. And let us keep this as a assignment for this week. And if you try, at least you try once, let it be wrong, then we can discuss, then it will be more beneficial right now.
Sir, only one feedback I want to give. Because see, we do not have everything in our fingertips like you, because you have more experience in designing. Okay, so I understand that you expect fast answers because you want to complete quicker, but we need some time to think and give a reply. And it cannot be both. It cannot be quick reply, and it cannot be also how to say this one. So please be little more patient with us because we are trying to learn also, right? That is one of the main things for these sessions. I understand that the interaction is more important. That is why we are continuously giving in chat. But it will be very difficult to give feedback and give answers at your speed of thinking because this is not our area of specialization for now. Okay, so please take that into consideration.
Okay, Raghunath. So let us keep this energy and let us go for the knee point voltage calculations. And I will take then this topic again. Okay, Raghunath.
Yeah, sure, definitely.
Okay, so please be active for this. And I'm honestly telling you, today discussion I'm going to do first time in my session. I generally not go in a such depth in my session because sometimes it bounds to the most of the participant and they feel that they do not know and they cannot learn. But I'm taking the risk that I wanted to keep the discussion in a more detail. So let us keep that energy and please open the mind. Try to understand. This is all is we should know as an electrical engineer. Okay, so we'll discuss this point. I'm not skipping this slide first of all. I'm not going to skip this slide, but I'm keeping this as a home assignment so that you apply your thinking, make a grid like that, take the study session as a reference, and then you do some mistake, and then we will correct, and then we'll discuss. I think that is fine. Okay, Raghunath, right now, and please be active for the please ready for the today discussion, and that is very important especially for me because I'm going to take this time in a session because that kind we take separate session and separate kind of participant we take for that for today's sessions. Okay, yeah. So let us start the city knee point voltage and understand overall the city knee point voltage. And let us start from the basic again from the scratch. So city knee point voltage, that is the agenda today. So what I'm trying to do, let me take one SLD if I have. Okay, let us take the study SLD only. VK is greater than should be star, I per star and RCT is star. So this 3 is star given here. Let us try to fill the value here like that we can say. So we are going to discuss only one word here and for that next 2 hours we are going to devote in that. So let us start from the basic. So what is the knee point voltage? First of all, let us know that, and after that we will do the calculations. So the CT knee point voltage, so the EMF induced in the CT secondary winding at event of fall. That is this statement, like I today added in my slide only at event of fault means the EMF induced in the CT secondary winding at event of fault we can say, and that is the point CT secondary winding. Let me draw the CT, the current transformer, this drawing that we have seen in the college time. So here my incomer bus bar, then breaker, and then it is going to be CT1. If we take one winding or we take max to max two winding, and then my this is primary P1 and then P2 here, and it is going to a load. Suppose load is my transformer, maybe then this is the symbol for the mutual induction. mutual coupling, and the CT secondary side more number of turns, more very huge number of turns based on the current ratio we take, and this is my S1 and S2 terminals. So, and these windings we put on the core. Right now there is a magnetic core, and on that this winding we wound, and that magnet and the this is core, and on the core we are winding this conductor, the copper conductor we can say. So the point is that the EMF induced in CT secondary winding, the this electromagnetic this voltage, the voltage induced during in this winding is the formula, the same college time formula we have put here, 4.44 5 ft2, where f is the frequency, this phi is the maximum magnetic flux in Weber, T2 is the number of secondary number of turns of the secondary winding. The flux in the core is produced by excitation current IE. This flux is in the core is produced by excitation current IE, or we can say the magnetization current IM, and due to that the error occurs in the CT also, because some part of current invest into the excitation or magnetization of the core, and after certain value of excitation current, the flux will, after certain value of excitation or magnetization current, flux will not further increase with increase in excitation current or magnetization current. This relation curve is called as BH curve, or we can the hysteresis curve for that core. Again, from the equation above, it is found that secondary voltage of current transformer is directly proportional to the flux F that we can see. This E is directly proportional to flux F. Hence, one typical curve can be drawn from the relation between secondary voltage, this E2, and excitation current, this I also. This I also. So that curve we can see by this secondary voltage, CT secondary voltage, and the excitation current A that we can draw. So when the excitation current or magnetic current is increasing, so initially the secondary voltage is increasing, and after the certain amount of time when the current increasing, then this flux is not further increasing, and the core comes into the saturation region. So, and this curve overall have the four regions from origin to the ankle point. This is the ankle point here, this one. Then from ankle point to knee point, this one. Then this is my knee region. This one we call as the knee region, and then it comes to saturation region. Saturation region means if you increase the current, then voltage at secondary side will not increase. That we can say this saturation region. Then the core of protection CT is made such a way, core, we are talking about the core of protection CT is made such a way that saturation level of that core must be high enough. But still there is a limit, as because it is impossible to make any magnetic core with infinity saturation level. And secondly, most important reason is that although the protection core should have high saturation level, that must be limited to a certain value. Otherwise, at event of fault, total primary current will transfer to secondary side, and that may badly damage to the protection relay. So the saturation is required in order to protect the relays. But what should be the saturation level when CT should saturate at event of the fault, at event of the huge fault? Therefore, in calculations, we wanted to know the minimum required CT secondary knee point voltage before saturations, so that the protective relay operate correctly and CT core have not been saturated at event of fault. So we can say that CT requirement is governed by the relays, and as per relay CT requirement, we need to calculate the CT knee point voltage. Am I clear with this statement? What I wanted to explain here with this statement, two things two things that if since CT work on the principle of N1 I1 is N2 is N2 I2. So number of tons already during the manufacturing it has been decided. So I1 is directly proportional to I2. So when the I1 increase, then I2 will increase. So if CT have infinity saturation, CT not saturate, so all the primary fault current will come into the secondary side. That is okay. CT is you will not your CT will not damage, but what will happen? Your instrument your relay will damage, and of course relay is costly than CT, right? So and if your like in your control panel may damage, there might be fire also in the control room building due to the higher amount of the current. So to avoid those kind of the saturation, CT saturation is also required to in order to protect the relays, in order to protect the meters, the fires in secondary site. But that saturation, how much voltage we require, minimum voltage CT secondary side is required at the event of the fault, so that minimum voltage after that CT may saturate. Okay, but minimum voltage required that will be governed by the relay, that to operate correctly the relay, how much voltage this relay required. And at the event of the fault, when the relay is operated, then it will give tripping command to circuit breaker, and circuit breaker will clear the fault. And then this CT will also protect it, and the relay is also protected. So the CT requirement is governed by the relay requirement. Each manufacturer, each company, each model have the relay have the different CT requirement. So based on the relay requirement, we have to decide the CT. So that is the reverse calculations that we need to perform.
Raghav, am I allowed to ask a question now, or do you want to continue,
Yeah,
and
yeah,
should I
tell
ask?
me. If this is concerned with that,
Yeah,
so
yeah, this is related. Okay, so I understand this, right? So the fault current is going to go through the security of the transformer, and you have uh, a burden or a resistor inside the relay, which is going to basically voltage drop. That is the voltage. Is that the voltage you are talking about for the CT saturation?
uh, actually,
Basically,
actually, what happens if we go to the relay catalog? The relay required some voltage. Relay coil. Here we have the coil.
hmm
So that coil, CT coil, that really have the CT coil and VT coil inside the
yeah,
ID, inside that ID, and that coil required to pick up
uh,
that coil. They required certain amount of the voltage.
yeah. But that voltage, where is it coming from?
That
My understanding is this from the secondary of the transformer
yes,
or
that
the
that
point transformer.
yes,
Yes. Okay, which
from
depends. Yes, and you have that voltage required. If it is generated, the only way it can get generated is you might have an impedance somewhere across it, and the
yes, the
current
city
flowing in
have
that
the
one.
city have the impedance, and this
Exactly.
R and this that button we will consider, and this cable also have some impedance. So all these
Yeah.
things we are going to add in the burden.
Yeah.
Yes.
Yeah.
So basically
No.
we are going to do, we can say that we are going to do V is equals to
Well,
YZ, and I we will take the fault current right now, not the continuous current. So I'm going to take the fault current as the I, and Z I am take the several
oh
Z
yeah,
I will take.
I
And
understand. Sorry to interrupt you, Raga. The only thing is, so the voltage across, say, that one, which is like, say, basically at this moment from your drawing, is I can say S1, S2. Considering all the cable resistances and
yes,
cable
this cable
impedances,
from
everything,
after S1 this cable, this not this one, because this is
that I can say that the voltage across S1 and S2 should not say 400, whatever the knee point voltage. That's what across. I can say that.
yes, 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 yes. Whatever coming, say 400 or 500, whatever coming by the formula, by the relay formula, that should be value of this.
Yeah. Okay. Okay. Thank you.
Yeah, relay burden parameters to be considered. Yes, Saurabh. To be, yes, we will take. Let us come on the relay formula, then we will see, Saurabh. Don't worry. Let me come on the formula first. We have not come on that. Okay. Uh, so far we are discussing about the basic concept. The basic concept is that basically in the CT sizing calculations, the formula I am taking from the relay, each relay manufacturer and each, even though one manufacturer, but each relay model have the different formula. So first of all, we have to decide the relay make and relay model, and after that we should go to the CT sizing calculations. And today we will take ABB make relay, and for that we will do the calculations. Okay. All right. So I think so far my point is clear. My point is so far it is clear. What is the C point, CT new point voltage? And here we decide one point till here that this the calculations we wanted to know the minimum required CT secondary new point voltage before saturations, so that the relay operate correctly and CT core not saturated at event of fault, and CT requirement is governed by the relay, and as per the relay CT requirement we need to calculate the CT new point voltage. So let us come to the CT sizing calculation for a transmission line protection relay. So what I'm trying to do, let us take the complete grid again. So let us take this complete grid again, and this is my transmission line right now. I might say this is my transmission line, this is my generator, and from here this is my transmission line, and then this is my substation, and this is again transmission line. So we'll take for the transmission line CT sizing calculations again, then we will go for the transformer also CT sizing calculation, and for bus bar also we will take. So the line, bus bar and trafo, that is the three main equipment that we need to protect. So for all the three we will do the CT sizing calculations, and let us start from the transmission line. Let us start from the transmission line protection CT requirement. So let us before going to the CT sizing calculations, and now I'm going to reverse again. Before going to CT sizing calculations, let us understand let us understand the transmission line protection, because protection relay selection. As I said in beginning, that CT sizing calculation is governed by the relay requirement. So let us understand about the relay selection, and after that we will go to the CT sizing, right? Please, like if you okay, then please see CR and see, so that I know that you are following me. If no, this is open, and you can stop me, and you can discuss with me. So I'm going like you can discuss with me. So just after your taking your point, we will go ahead. So the transmission line protection, for the transmission line, uh, see we have a separate model for the protection. As I will show you in the service also, we have a separate model of the protection. Where is that protection? This is the services and transmission and the feeder protections. Relay metering SLD preparations, relay for this. All these things we have for with respect to the relay. But before uh, today only I'm going to take the relay that is required to understand the CT sizing calculation, that much only. So if any point you are difficult to understand, don't worry. Again we are going to revise all these things in a detailed way in the protection module. Okay, so this is not the protection module, this is the CT sizing session, but again we wanted to go from relay then CT. So transmission line protection, for the transmission line, there are two kind of protection used in power grid, and I think we have some protection engineer also right now. I think Raghunath, you the protection engineer who can add something in this slide, so it will be better. Yeah, yeah, Soumya. So I think also you are also there. So you both protection engineers. So please add anything, or you can explain the point as per your understanding also, so that others can easily understand. So for the transmission line, there are two kind of protection used in power grid. I mean to say, this is my power grid. This is my power grid network. So two kind of the protections we use for short transmission line. for short transmission line length. But if I'm telling short transmission line length means this one, this line length is less, this line length from here to here, less line length, so that is the short transmission line. So for that short transmission line length, the line current differential protection as main protection system, and for this line differential relay used. That is the statement number 1. Second statement, for medium and long transmission length, the distance protection system and distance relay use, and this distance relay called as impedance relays. Why this is called the impedance relay? Because it measures the transmission line impedance value, and if measured impedance value less than set impedance value, then the distance or impedance relay operate. So we discussed here that two type of the protection we do for a transmission line, and that relay selection is depend on the length of transmission line. For short, line differential; for the medium and long, line distance protections we take. Now in few utility, for short transmission length, mostly both the protections, differential as main protection and distance as a backup protection also used. And in this case, we need to select relay model that have both protection function, means that have the differential protection function and the distance protection function also. Now let me ask one question to the protection engineers, that for the differential, for the short transmission length, why we go, or why you go for the differential protections, why not distance? Generally you refer.
Yeah, the main reason we go for the differential protection is, suppose for example, short line. What we refer to as short line is for distance is less than 5 kilometers, for example. So what will happen is, as we have already seen, we have errors in CT. Okay. So in case of transmission line protection, what we cannot the transmission distance protection is basically not a unit protection. We have made it unit protection forcefully by dividing the distance protection into zones. Okay. So what we do is zone one, that is the trans. We take only 80% of the protection in our side and another 80% of the protection in the opposite side. That is the reported. So if the line length is very very short, the fault may occur in the middle, and the relay may not be able to find out exactly where the fault is occurring because of the CT errors. So that is a problem.
Correct, correct. And one more point, let us add. Silpa also very correctly add one more point. Fault location is not an issue in the short line, because the line length is 5 kilometers, say 10 kilometer. In that case, the fault point, the fault location point is not any concern. Any O&M engineer can easily go 5 kilometer and they can trace out where the fault have happened. So both point, as Raghunath said and as Silpa said, both point we can add. And one more point that I wanted to add in the same reply, that in case of short transmission line, the line conductor resistance and the line conductor reactance values shall be very less. So measured impedance value will be very less. We can say less than 0.5 ohm. Due to this reason, the distance impedance relay may malfunction, because the impedance measured value is 0.5 ohm, 0.3 ohm, 0.2 ohm. So very less impedance they are going to measure for short transmission line. So due to this reason, the distance or impedance relay may do malfunctioning for the short transmission line. Therefore, for short distance, we take differential relay as a main protection relay that work on current differential principle, and in backup distance protections may use as a additional backup. And if I'm telling short distance, so as per India, as per the CEA, Central Electricity Authority, they have defined the limit as 30 km. Less than 30 km differential relay as a main protection relay and distance as a backup relay we use. This is a statement given by the CEA. Okay, so if anyone telling that short length means how much you can take, so max to max 30 km. Beyond that we should go distance for sure. Okay, less than 30 kilometers. In that case, since the line length is less, line conductor resistance value will be less because the line length is less. So the measured impedance value will be less because the less distance of less conductor length. In that case, the this distance relay may malfunction because CT error and VT error also we have to include. So already very less impedance coming. So therefore, for short distance, it is recommended to go with the differential relay, and on that we can add both point as Silpa said. Yes, yeah, yes, we'll come on that Krishna move relay and quadrilateral. That all we are going to discuss in the distance relay calculations. Okay. So yeah, so low impedance and fault location is not an issue for the short line. For the short line, I hope this statement is adding one more point. So here we discuss about the protection. What kind of the protection required? Now, based on the protection required, let us do the selection of the relay. So now based on the required type of the protection function, differential and the distance, two protection function we discussed for the transmission line, the relay model need to be selected. The available relay model type provided by the relay manufacturer and also that can be found from their websites, that what type of relay model is available. If we take ABB manufacturer, they have the RAD670 relay model. In this RAD670 relay model, both differential protection and distance protection function are available in one relay unit. So if I am going to take that short distance, if my distance is short, I will take the RD model and we can use the both type of the protection. So in that case, I can take the RD670 relay model. So let us have a view of overall relay models. So this is the overall relay model. I'm trying to keep this session very simple so that if anyone new in this power system and if anyone not the protection engineer, they can also understand. So I'm just trying to keep it very simple so that anyone can understand. Yeah, in Schneider we have P4, P4, 543 and 546. Correct, Somya. In Schneider we have this. In ABB we have RAD 670. Okay, so let us take this one. So please do not think that you are not production engineer, so you cannot understand this. I'm trying to keep it very simple and anyone can understand. Just please follow me. So this is, I have taken the overall relay, I have listed out and take a snapshot. So as per the ABB, we have the R500. So here we can see the applications, and here we can see the type, and here we can see the relay model. Application: feeder protection, bay control. This is all my protection applications. So we can do the feeder protection. Feeder protection, if I am telling, so what I am referring, basically I am referring this one. This is my feeder protection. This is my feeder protection. So for this feeder protections, what kind of the relay we will take, that we can see here. We will take for the feeder protections what this no 630, 620, 615. These are model we can take. And before this number 630, 620, 615, before this numeric number, we have to add one alphabet, that is REF. So REF 630, REF 620, REF 615, REF and 611 we can take. In generally, let me tell you what we can take and what generally we take. So generally we take REF 615, this model, for any distribution feeder protections right now. Or anyone have any additional selection they can add on? Because I have taken 615 so far, that's why I quoted 615. RF615 we generally take for the feeder protections. When it comes to bay control, then the type of the relay is changed from REF to REC. This is only name given. Do not apply any mind here. That is the only catalog I have taken and I paste here. So this is no any mind. This is only your knowledge, and you can memorize this model. Okay. Yes, Mehul. REF615 is more famous. So that the same as also my opinion. REF615 is we take. Okay, so when it comes to bay control, then we take REC, and again many options we have, and generally REC670 is more famous. So REC670 we take for the bay control. When it comes to transformer protection, then means when it comes to this trafo protect, this is my trafo. So when it comes to this protection, so what relay model we take, that is this RET. Please note down this value, because when I will go into E tab, when I go in E tab and relay coordinations and relay sizing calculations, then I will take the model directly from the ETAP library. Then at least you should know the name, what model we take, so that we can easily take from the library. So for the transfer we take RET model. Again 500, 670, 650, 630, a lot of model available. Generally we take, I think, RT670, right? Traffic protection. When it comes to line distance protection, then REL. REL 670, 650, only two model available. And let me tell, the mostly we take REL 670, the line distance protection. That is both we can take, but this is more famous. When it comes to line differential protection, then we take RED. D stand for the differential. So RED 670, RED 650, this, and RED 615. This three relay model available. There is no relay model available. And mostly we take RED 670 because that is more famous, and I think that have both the function differential and distance also. You can see many applications: motor, generator, bus bar, capacitor, breaker, voltage, this all, and you can select this relay models. So what is my let me draw the now one network also. If so far anyone have any difficulty, let me know. I'm trying my best to make it very simple. So what we discussed so far, we are discussing about the CT, knee point voltage, CT knee point voltage. And the first point, the CT knee point voltage, we will call as the KPV, right? Knee point voltage. K stand for the knee, P stand for the P, and B. KPV. Let us take this short name that generally we take also. So KPV, we are calculations, and for that we discussed that CT knee point voltage shall be governed by the relay model. That the relay model will be governed by the relay model. So now we are discussing about the selection of relay model. We are discussing about now selection of relay model. So for the relay model selection, we should know about what is the protection function required. Protection function required, that we discussed. Protection function from the relay required. So, and now we are taking the case, that the case is transmission line. Transmission line, feeder the REF 615. Okay, feeder, not feeder, any transmission line we are taking, transmission line. And for this transmission line, we require two protection for function. One is the line differential, and second is the line distance. Right? So for, and here we discuss for the short line. For the short line we take both line differential and line distance, both we take for the short line, and for the long line we take only line distance. So let us start from the short line. So we will take both line type, and let us start from the short transmission line. So that we discuss both type of the relay. So CT requirement for the differential and for the distance also. So this distance will be covered this distance also, short transmission line. We want to take both case. Okay, and and now we, for the short transmission line, we are taking the RD670 model, because this relay model have both the function. I will come on that relay catalog also, so that we can see the RD670 that have both the functions. So I think so far everyone is clear what we discussed. Let us go point by point, and so far it is clear to everyone. So now based on the protection function requirement, we need to select the relay model from above available relay list. And once the relay make and model finalized, then we need as an input relay application manual, and that application manual can be downloaded from the ABB library online. We can go and we can download from the ABB library also. And this relay application manual have many pages, around 200 to 400 page document we have in the relay manual. So no need to go all 400 page, directly go city requirement page, and from index and note down the city requirement formula from the relay manual. Let us see and let us go and let us download. Yeah, so yes, Siddharth, as a backup only. Yes. So we are going and we are downloading RED 670. Now there is many manual. Okay, technical manual relay. This is. Please go very specific. Go to the application manual, because if you download any other manual, you will not find the formula. Okay, so write up APPLI application manual. Otherwise, you will not find the formula. RED 670 application manual library, ABB library, and same we can do for any make model, ABB make, RCMS make, any make we can do. Now this is my, so first of all we should know the relay, this one selection we should know, and before the relay selections we should know the required protection type. So this is my what is the name here, RED670 line distance, distance. These are the features: order close, supervision alarm. Okay, main bus 1, main bus 2, isolated. Okay, so line differential protection RED670 application manual. Again 724 page. No need to study 724 page for the city sizing calculations. Directly go to the city requirement. City requirement. City requirement. So introduction, requirement, current transformer requirement. I am directly going on the current transformer requirement. The performance of protection functions, this also is given, and now directly go to the formulas. Fault current, secondary winding resistance, and additional load on. Okay, general current transformer requirement. Yeah, rated equivalent secondary EMF requirement. That is my point. Rated equivalent secondary EMF requirements. With regard to the saturation, now they are again talking for the saturations. With regard to saturation of the current transformer, all current transformer of high remanence and low remanence type that fulfill the requirement on the rated equivalent secondary EMF EAL below can be used. The characteristics of non-remanence type will be okay. The city requirement for the different funds may be also specified as a rated equivalent limited secondary EL according to IEC. Also standard requirement cities specified in a different way are given at the end of the section. So line differential protection. The current transformer must have a rated equivalent. Now you see the CT is sizing is provided by the relay. The current transformer must have a rated equivalent secondary EMF EL that is larger than the maximum of the required secondary EMF EAL required. Okay, EAL, this is the CT new point voltage, should be greater than or equal to EAL required. And there is many formula. So all the formula based on the productions we have to take, and the largest value we have to define. We have to select for the EAL. So equation 1 is what? IK max. And if you see this formula overall, what I am doing, E V is equals to IZ, right now. Kamis, that you asked me, V is equals to IZ. I is fault current and Z is this Z. Okay, so yes, let us understand now this. E I K max ISN IPN RCT plus RL plus SR plus IR square. In that IK max is what? That is the maximum fault current. ISN is the secondary rated current, IPN is the primary rated current, RCT my CT secondary resistance, RL is my load cable resistance, and SR is the relay burden, RB, relay burden, and IR is the again relay current. Relay current will be series secondary current right now. So this ISN and this IR will be same. Can we say like that or not? Yeah. So equation 1 is that. Now if you see second formula, that is 2 into IT max. So what is the IT max here? IT max is the through fault current and maximum through fault current. And other is clear. We can see this also here. They I think they have given the this, where is that page here? There are many page. So CT, yes, coming on the CT. Yes. Now you can see this is the line differential protection, and in the same RD 670 model, we have the line distance protections also. Okay, and suppose if I'm using this for the long transmission line, so I will go only for distance protections. I will not go for this above formula, but we are using both differential and distance, so we will perform calculations by these two equations and these two equations also. So both all four we have to consider here. So this where IK maximum fundamental frequency fault current for the internal closing fault A. So IK max value given is that IK max is what? Maximum primary fundamental frequency fault current for internal close in fault A. So it means maximum fault current for the close in fault. Close in fault means fault within the substations, we can say, right? And that is the close fault to the near to the CT. Am I correct or not? So the IK max value, can we take the maximum fault level of that substations? Should we take or not? Suppose my fault level of this substation is 63 kiloampere or 50 kiloampere. So I will take the 50 kiloampere of if the fault value of this bus bar or the fault value of this switcher is 50 kiloampere. So IK max I can take 50 or 60, whatever the maximum fault current. Right now, how to select the fault current? This point already we have discussed. So anyone have any query in the fault current selection? Fault current is clear to everyone. I hope so. Right now, fault current selection is clear to everyone. So that fault current will be my IK max. So IK max, no need to explain. This is clear. IT max, maximum primary fundamental frequency. Please forget about this tough word, primary fundamental frequency. Delete this all. No need to. Point is that for through fault current, for external fault means this relay taking two amount of the fault current, because one is the closing fault, one is the max this fault, external fault, not to this substation, to the external locations. When the fault occurs, then what is the maximum fault contributed by that external fault to this towards the city? So that fault current we need to take as the IT max. IP is the primary current, ISN secondary current, IR is the rated current of the relay, that will be the ISN, RCT circuit resistance, R is the lead resistance, SR is the relay burden. So what is the relay burden? SR, the burden of ID, current input channel VA, SR 0.020 VA per channel for IR1 amperes. So SR will be 0.150 VA per channel for, so SR will be 0.20 because my IR is 1 ampere, right? This 3 and 4 no need to consider. Why not required to consider? I will come on that later on, but it is not required to consider because they are telling the case when the fault current is not passing, uh, uh, fault current may pass to main city for the line in a subsystem with breaker and half or double bus bar double breaker arrangement. The through fault current may pass to main city for the line differential protection without passing the protected line. So generally it is not happening that city fault current is passing city but not passing to protection line. So that is the reason generally equation 3 and equation 4 we not consider mostly. Then equation 5 and 6 again this IK max ISN IK zone 1 ISN IPN. So this A and K. So in this calculation mostly we should know about the A, K, IK zone 1, and in above equations we should know the IT max. So if we know this value we can easily calculate the line of the required knee point voltage right now. So I have taken this snapshot and I pasted in my for in my presentations here. So the line differential relay CT requirement calculations, line differences equation 1 and 2 I have taken and pasted here, right? And same already we have seen IK max to IT max. This all already we have seen, right? SR is 0.20 VA that we have to put here. So let us come and what we discussed here that in difference. So let us go first this. Okay, let us go first this, and then we will go on the distance. So first city sizing for the differential protection relay function, right? And after that we will go the city sizing for the distance relay function. And out of the four equation, which one provided the highest knee point voltage that we can take as the city knee point voltage? Right now I think the approach is clear. The approach is clear. So we'll go one by one. Let us go by first this, and then we'll come on the distance. And there is four value we will calculate as we can see here. Let me go already 670. So I am calculating the four value, one here, then 2, 3 and 4. 4 for the differential because 2 current, and similarly I think 1, 2, 3 and 4, big 4 here because 2 amount of the primary current, that is the reason. So total 8 value we are calculating, and which one provided the highest voltage that we are putting as the highest voltage. So out of this 4 the highest one, and out of this 4 the highest one, that is my recommended KPV knee point voltage, right? So we have to perform all the four calculations, and we have to see that which in which case the required knee point voltage is higher, and that will be the city knee point voltage. So let us come to the case 1 first, and then case 2, then equation 5, 6 and all that we will go. Yeah, so we can see in line differential relay equation, as we know that there are two type of the fault based on the location of fault. Now I'm trying to explain the formula with the backup with the statement with some concept. So the case 1, close in fault near to substation, and so should take full amount of fault current in calculations because that is closing fault. So IK max will be my full amount of fault current after substations. Second, IT max, any external fault or remote end fault that may reach till substation are called as through fault. I mean to say fault is happening suppose here, and that fault through this conductor may reach here also. So this case also we are taking, right? So two amount of the fault we are taking in order to decide the city knee point voltage. we are taking the fault current, okay, because at the amount of the fault current CT may saturate. So we wanted to take that before CT saturate, when the fault is happening, before the CT saturation the relay should operate. So we are calculating the that how much voltage required relay to operate, and that voltage we are keeping as the CT point voltage. So every time we will not take the full load or continuous current. Every time in this calculations we will take the fault current only. So why fault current? I think this point is clear. Why we are not telling as the full load current? Why every time we are telling as the fault current right now? If not, if anyone facing difficulty, why I am telling fault current, please let me know. Is that clear? Why I'm referring the fault current, not the full load current? Yeah, Ravnath, yeah, this is clear to you, but what about the other engineers who are not from the protection background? Yeah, so please concentrate again. What we discussed here, when the fault current is flowing, when the very huge amount of current flowing, this CT, then this CT core, because core is made of the magnetic material, right now, magnetic material or iron you can say. When huge amount of the current is flowing, then this core may saturate, and when the core saturate, then it will not produce any magnetic field, it will not produce any flux, and then it will not generate any current or voltage, okay. And this will happening when the huge amount of the fault current, and that is the my fault, that is my the fault current that may flow. uh, so that is the reason I am taking the fault current in the calculations. I think this is clear to everyone. uh, Fault current, why I'm going to take the fault current. Yeah, so an external fault or remote in fault that may reach till substations are called as the through fault current. For differential relay, the required voltage, by relay are required CT knee point voltage we have to calculate for both type of the fault locations. For closing fault this formula, and for through fault this formula. Right, so yeah, closing fault and the distance fault we have seen already. Closing fault here and through fault here. External fault or remote in fault we can say. So basically we need to two set of calculations, or we can say the relay manual consider two type of the equation for city requirement calculations. First condition for the fault within the substations, and considering the maximum fault current value flowing through the CT core at the substation's location, and also called as the internal closing fault. Second conditions in the formula for the fault at the last point of our production of the last point or the last portion of the protected conductors, that we can see here. This is my sending. This is my substations. Here we have CT, here we have the breaker. So if the fault happening here, so that is one case, and this is my outgoing transmission line, and this is my receiving end substation. Second case, that fault happens here, then this location we call as the second conditions, we call as the remote end fault, or the throw fault we can say. The last point of the protected last portion of the protected line feeder. Now in this case the transmission line impedance going to add this line impedance ZL, that going to add in total impedance, and based on the line impedance we have to calculate the through fault current. So we'll calculate the through fault current. Okay, first of all, what is the through fault current? This statement is clear to you or not? Through fault current is what I mean to say through fault current. uh, Let me take, if I can take the ETAP also. Just give me one moment. Yeah, correct, Sivam. Outside the protected zone, we call it the through fault current. Correct. Yes, your statement is very valid. Just uh, some Rohit, please mute yourself here. Is it possible to do some simulations? I don't know. Can I do here? Yeah, that bus is also horizontal fault. There are a lot of cases. Here, don't fault. Means can we do? Yeah. So what I'm going to do here, let me take two bus. My sending in substation here, then one bus bar, then transformer. Then here we have this secondary side of the transformer, and here we have secondary bus, and here we have one lump load. So what I mean to say through fault, let's take one another example. This is my trafo. So if the fault happened on the secondary side here, if the fault happening, let me generate the fault. It is already faulted, so let me do fault. So if I put fault here, so how much fault is coming at the HV side of the transformer, that we can say the through fault. So if I run the fault here, it is coming 43.9 or 44 kiloampere, and due to this fault on the HV side of the trafo, 10 1.06 kiloampere fault is coming right now. So this is 1.06 kiloampere fault coming at the HV side, even though there is no fault happened here. Fault happened here on the LV side of the trafo, but some amount of fault current coming here. So that amount of the fault current we can say through fault current. Am I clear what I'm trying? What is the through fault current? The here we have one line. This is my substation here. Send one substation here, and there is a line. It is going to here transmission line. Or that we can take this one also. Let me delete. Uh, delete erase all these things. Yeah. Just give me one moment. Yeah. So yes, weakness. So I think this is clear to everyone. So I'm putting the CT over here. My CT is over here. So I'm taking the fault current of this closure fault, the fault happening here. Then how much current flowing through the CT. Second case that I am taking, if the fault is at this side, then how much fault feeded by this locations to this substation, and that we can say remote fault, that we can say the remote in fault, are the same we are telling as the through fault. And that this is point example number one, and this is my example number two right now. And here we have calculated the amount of fault current also. Yes, correct, Siddharth, due to the turns ratio only. Yeah, okay. Now it is very clear that when this throw fault, this fault is the IK max, and that is my full fault of this substance, that we can take 63 kiloampere or whatever the maximum fault of this switchyard. And when we comes to the remote in fault, and that fault we have to calculate also, okay. So that is that need to calculate, and that is already given in the tender specifications. So during this fault calculations we have to add how much voltage is coming, right, and how much is the impedance added by this line, because here is 63 kiloampere fault, but when we go uh, travel through the line, so line conductor have some resistance and reactance right now. So due to that line impedance, line resistance and reactance, this value will be lower, less, the fault current will reduce here right now. Am I correct? Due to the line impedance ZL, because you are adding the impedance. So here here we have, yeah, so let us understand, or let us do some exercise for through fault current IT max. So basically this IT max I'm going to put here. Okay, this IT max I'm going to put here, but before putting the IT max here, let us understand overall about the IT max. Overall understanding let us develop, and then perform the calculations, and then I will put here, and then we will perform the final calculation. So coming back and understanding this, yes, there will be voltage drop, sure. Yes, but at the same time the line will induce some reactive power, Siddharth. Okay, so whatever voltage drop happening due to the line reactive power, it is boost up, so don't worry about that. And for that you can refer the Ferranti effect, and that we have discussed in class day 2. Okay, yeah, so for through fault current ITMX, for differential relay CT equation, the through fault current calculation is required. For the distance it is not required. If we go to the distance, you can see ITMax is not the part of distance. So if I'm doing the CT for the distance, then no need to calculate through fault current. You can see there is no any IT formula here. Only differential required, the IT. Through fault required in case of external fault or transmission remote end fault. Since the current oblique, we can say the fault current depends on the line conductor resistance and reactance, or we can say the total impedance value of the transmission line. So we need to calculate the total resistance and total reactance at the fault location, and based on the resistance and reactance we know the voltage, we can find out the fault current, right? So first of all, before calculating the current, let us find out how much impedance added, how much impedance added till here, and based on that we can calculate the fault current also. So uh, till the fault point, till the fault point, till the here, what will be the total resistance? And let me tell one more point, let me tell one more point. uh, Before this substation, yeah, please concentrate, this is very typical statement, and that going to decide the calculation approach. Okay, so see, uh, this this generation, so I am going to indicate this generation by this here, this symbol, my generator, and we are feeding the power, voltage and current two-way substation. So this substation I'm going to indicate as a bus bar, right? This bus bar, this one, we can say this bus bar, like, or you can say anyone. And now from this bus bar we are sending, we are putting the this breaker and CT, and now this is my transmission line, and that is going to the next substation here, and here I am putting the breaker and CT also for this transmission line protection, right? So, and now we are calculating the fault, we are doing the CT sizing for this one, suppose, for this one. So one, we are taking the fault happening near to the substations, and second we are taking that fault happening to this locations, that is the remote fault we are telling, or through fault we are telling. So if we take overall, so in the entire network, what is the source of fault current? What is the source of fault current in the entire network? In the entire network, source of fault current is what?
Generator.
Obviously, a generator is my source. Source is the generator. So generator is my source. So the fault current is source is the generator of the fault current also, right? Because when we go away from the generator, the fault current value will be lower always, because we are putting the line. So it will be the source of fault current is the generator only. So now till here till here we have the two type of the resistance. So what we are doing till this point, till this subsistence, we are taking the fault current as per as given in the tender specifications. Suppose 63 is given in tender specifications, so we are going to take 63 kiloampere till this point. And till this to the remote point, there is two kind of the source, there is two kind of the resistance. One is the source resistance, that value from the generator as a source. One is the source resistance that is coming till here, source resistance. And second, we have the let me tell as the rs, source resistance, and the and x source reactance. And one line impedance value we have as the line resistance, rl, and line resistance, uh, rl, and the xx. So there is two type of the resistance and reactance: source resistance reactance and the line resistance and reactance. So if we wanted to calculate the fault current till here, so we have to add both the value, and based on that we have to calculate the total impedance, source plus line, and based on that we will calculate the fault current value till this point. So total impedance, we need to calculate the total resistance and reactance at the fault locations. So total resistance means total, since my fault source is the generator, so that is why I'm starting from the generator now. Total source resistance from generator. Please do not ask that what is the source resistance, that I will we will find out based on the voltage and fault current. So I will calculate this also. Okay. So total resistance, total source resistance from generator till the substation, till this substation right now, till this substation, plus connected transmission line resistance. Total reactance, total source reactance, plus connected transmission line reactance. Am I correct with this statement? I don't know what is the like till here we know the 63 kiloampere, right? I don't know that what is fault current here, 80 kiloampere, 90 kiloampere. I'm not aware about that, because that value is not given in the tender. The value is given for my substation voltage and that fault current. So my 400 kilo voltage, if we take, so for the 400 kilo voltage, as per the CEA, let me go, let me show you the CEA also. Okay, please develop your understanding. Let me go to the CEA. What is the CEA standard? And yeah, CEA. And then let me take the fault current based on the voltage wise. I don't know that what is the length of that, what is the location of that substation from the generator, how much away they are placed. We are not aware. So for 400 kilo voltage, you can see how much, 40 and 63 right now. Two fault current is available. So, and the higher fault current will give the higher city's NIP and voltage requirement. So I will take highest fault current. So I will take 63 kiloampere fault current till here. So where is my point, right? I don't know this length, I don't know this source resistance reactance also, but till here the fault current is 63 kiloampere. It might be come from the one generator, it might come from the two generator, it might come from the fourth generator. I don't know about that, because we are not have the complete grid, because we are doing the project for one particular substation, right? So we will take that fault current at the substation location, right? So 63 is where at my substations. If I'm going away, it will reduce, it may reduce, obviously it will reduce because some value we are adding. but how much reduce, that will depend on the conductors, this one also. So yeah, I think this is making some sense. So yeah, total resistance and total reactance. So let us go first to the source. uh, Resistance, source reactance, and then short circuit current nature. So before calculating the source resistance and source reactance, we should know the nature of fault current. What is the nature of fault current? So before calculating of source resistance, source reactance, and through fault current, we should know the nature of short circuit current, and from that we can find out the source resistance, reactance, and impedance. At event of the fault, the actual short circuit current consists of two components: the sinusoidal varying AC component, one is that. Second, at event of the fault, the total fault current have the exponential decaying DC component with a time constant based on the system inductance and resistance value, and a bottom and top envelope, that is the short circuit current value at that instant. Let us see this statement in a graph. This is my fault current nature. This is my event of the fault, as you can see here. Okay, so when the fault happened, A is what? Initial value of DC component. Okay, this is A. IP is the peak short circuit current. Peak short circuit current here, this one. So when the fault is happening, this is the instant of the fault. So this is my uh, maximum peak current. Then it is, you can see there is a sinusoidal AC component that is coming like that, and plus the fault current have one DC component, IDC of the short circuit, that you can see by this dotted line. So there is two instant, the AC plus DC, and we have top envelope that you can see here, and we have the bottom envelope. Bottom and top envelope is that the amount of total fault current at that instant. So this instant, this is my maximum uh, peak, and this is my minimum. So that is the this is my point of amount of short circuit current at that particular peak, and that peak we are adding. So we are making one, we can draw one top envelope and we can draw one bottom envelope. So total at instant of fault, there is two component we have, AC and DC, right? And the DC component depend on the resistance and the this DC component with a time constant where system inductance and the system resistance. It depends on these two value. What is the system inductance and system resistance? If system have the higher inductance and higher resistance value, then it more DC component will come. First of all, why DC component comes in the AC? Why DC component comes into the AC? Uh,
Because because can you hear me right now? Hello?
yeah, yes. Really,
No, well, it depends on where exactly the fault occurs. If it is a zero crossing of the voltage or some other point. If it is occurring at some other point, like say peak, you get at the peak of the sinusoidal voltage, you get the maximum DC component.
yeah. So let me add one more point as per my understanding. What is my understanding? Let us take the transmission line M4EL model in power system. Yeah, that we can take image. Yeah. So when we see the transmission line have the inductance and the capacitance and the resistance. So we know that the inductance and capacitance store the energy right now, and inductance store the energy half Li square. How much energy they store this inductance, and I think the capacitor store the energy half CV square. I'm not confirmed about the formula of this.
Yeah, correct.
So when any inductance and capacitance, when they are storing the energy, and when any short path happened, so what they will do, they will immediately discharge that energy. Right now, they will immediately discharge. So we can take any capacitor as work as a like battery, you can say battery, DC source, and they will immediately discharge that energy. So when they are discharging the energy, they will not follow the AC sinusoidal, right? And they will follow the DC. They will whatever this energy they have stored as in terms of the half Li square in case of the inductors, or half CV square in case of the capacitor, they will discharge this energy. So first of all, they have the higher energy, they have the higher energy, and uh, and with time they are discharging the energy, and after some time it will come the zero. So this waveform, it will not be sinusoidal, it will be this exponential decaying nature it will come, and that we are telling as the DC component. Right now, I hope this is one of my understanding. If you have any other that you can add, but I think that what should be the source, so that I think that is the source. Yes, correct. Inductance. Yes, inductor behave like a battery source during the decaying component in the RLC circuit. That is the point. Oh, just give me one moment. My mouse is not working. Okay, mouse is not working. Anyway, yeah. So this DC component will come. So based on this DC component, we will find out the XL and R value that we are going to find out. So we are going to basically the reverse we are doing. So So, as we know that when any short circuit occurs, the total short circuit current consists of the AC component that varies sinusoidally with the time, also known as the symmetrical current, DC component that non-periodic and that decays exponentially with the time constant Tp. For Tp, the time constant depend on the L and R of the system. So where L is the power system source inductance and power system source resistance is the R, and therefore with help of L by R we can derive the power system source X by R also, X by R ratio also, because L is what? L is 2 pi FL, like X is what? XL is 2 pi FL. So with help of L by R we can derive the X by R, power system source X by R ratio, because X is 2 pi FL. So X we can L we can write as the 2 pi FL divided by R. So L by R is this one, and 2 pi ft. So this 2 pi f and LR is the time constant. LR is the time TP is L by R. So with help of L by R we can derive the power system source X by R, and since uh, X by R is the source reactance and resistance ratio we can derive with, and X is 2 pi FL. So 2 pi FL divided by R. L by R we will take separately, so this we can rewrite X by R as the 2 pi ft, and thus we can see that the source X by R ratio will affect the DC component time. With help of X by R ratio of a circuit, the longer the DC component, it will take longer time to decay, at longer time constant we can say. So we are going to derive the X by R, and with help of that we can find out the source resistance and reactance value. So far it is clear to everyone. DC component, so we are calculating that how much time required to decay the DC component, and that time is L by R. Just give me one moment. Yeah, no, mouse is working. Yes. Yeah, we can do. Okay, so let us now perform the calculations to find out the TP, time constant. So in order to find out the time constant, we have to refer this DC component. And as in substation, the circuit breaker used to break the DC component for short circuit current along with the AC component. So there is one important point when we are selecting the circuit breaker. Please do not focus only on the AC breaking capacity. We have to also check what is the circuit breaker DC breaking capacity, right? So DC breaking capacity, how much they can handle. The DC component breaking capacity of circuit breaker can be taken as input from CP circuit breaker manufacturer technical data sheet or circuit breaker rating plate. So that we can see here. This is my ABB high voltage uh, rating plate, and in this rating plate we have these all informations, and on that there is a DC component breaking capacity that is 61 percentage. So that 61 percentage circuit DC they can break, and 61 percentage is fine because what will happen, a circuit breaker have opening time that is the 40 uh, because 40 millisecond. So when the fault happening, then after 2 or 3 cycles the circuit breaker going to operate. So 61% is also acceptable. So circuit breaker breaking capacity 61% is that they can break, DC breaking capacity, and circuit breaker opening time, that also we can see what is circuit breaker opening time, that we have to check from the city rating plate, sorry, technical data sheet. Circuit breaker opening time or breaking time, that is 40 millisecond. That this breaking time we will discuss in breaker session also, that is the next circuit breaker selection sizing, that we will discuss that time also. So circuit breaker breaking time or circuit breaker opening time we can say. So these two parameters we have to take from circuit breaker technical data set in the CT sizing calculations. So the percentage is the component that can be taken by above, and by below equations we can calculate the DC time constant. So the TP time constant is equals to T. This T is the tau, basically tau divided by under root 2, tau divided by ln log under root 2 divided by percentage DC into 100. So in my case my breaker timing is 40 milliseconds, so T will be 40 milliseconds divided by ln under root 2 divided by 61 into 100, and it gives TP 47.57 milliseconds. Just we need to derive solve this, and it will give the this time constant TP, right? So this is my breaking capacity for a 252 kilovoltage breaker, and similarly we can see
Aga,
the DC
sorry
component
to,
for a 500 kilovoltage circuit breaker. Yes.
no, sorry to interrupt you. Regarding the last point, so you said like a breaking point. So the last point, the breaking time, which is circuit breaker breaking time, is 40 milliseconds. But in actual case, like say, either do I take this whatever mentioned in the data sheet,
Yes.
or do I have to actually say the calculation of like relay detection time and
No, 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 no.
load?
That is this is not the relay detection time, relaying time. This is the breaker opening
Okay,
time.
it's just a, okay, it's just a circuit breaker opening time.
Opening
Okay,
time.
thank you. Yeah,
That we are taking.
okay, thank you.
Okay, but we can take that one also. That one also, because when the fault is happening, relaying time generally we can take 10 millisecond, 10 to 20 millisecond, and the breaking time we can take 40 milliseconds. So we can take 50 or 60 millisecond. We can add that one also. Uh, the total breaking time, considering the breaker and plus relaying time, right now. So that we can take total.
This is a little bit. I do not want to deviate it. I understood, but my question is like, say, for coordination purpose, I will not check the. I will not take the instantaneous one. So if I have say 300 milliseconds opening time of that particular breaker, so yeah, my use 300 milliseconds to calculate my time constant of the
No,
system.
no, no, not 300 millisecond, because
No. What I'm saying is the query I have is I understand what you just said, but you have a what we call is short time and instantaneous and long time protections. Okay, so if for coordination purpose we can, or you can say definite and or we call it instantaneous. So instantaneous instantaneous protection, if I disable it and do not use it, then I can adjust my opening time of the breaker for coordination purpose. So if I do that, do I have to take that time opening time of the breaker, or do I still go with the 40 milliseconds?
actually,
If I confuse you, leave it. If I confuse you, leave it. I will ask you, and
no, no,
just carry on.
let me add one point, as Somi also replied. When it comes to distance or differential relay, their relaying time is very less, like 20 millisecond, as Somi mentioned. Generally, relaying time is 20 milliseconds. Generally, not more than, because distance and differential both are numerical relay, and that is not coordinated for 300 millisecond or 200 millisecond, because you cannot go more than 100 millisecond, otherwise the power system will not be stable, so there might be stability problem. So due to that, we cannot go very long time.
Okay.
So generally, the distance and difference relay operate in 10 to 20 millisecond. So relaying time 20 millisecond plus breaking time 40 millisecond. If you wanted to keep it max to max, so that time we can add, and 60 millisecond we can take overall.
Understood. Thank you.
Yeah. Okay, so coming back, so by taking this DC capacity, why DC breaking capacity we have taken here, as I said, because when the fault happens, there is DC current also. That is why this DC breaking capacity, and the breaking time 40 millisecond, and based on that we can calculate the time constant. So based on the time constant, we can find out the X by R. Let me show by this page. So this is my breaker rating plate for 252 kilovoltage. This is my breaker rating plate for 500 kilovoltage. And you can see the difference. In 220 kilovoltage, the DC component is 61 percentage, and here the 500 kilovolt DC component 56 percentage. So each voltage, the DC component may vary. So please refer to circuit breaker actual, whatever circuit breaker you are using. Please refer that actual circuit breaker rating plate, and from that plate you pick this value. Okay, the 61 is not the cost, is not the fix. That may change with respect to the breaker voltage and breaker make. So please refer breaker rating plate and pick the DC component, and that use in the formula. So if we take 220 kilovoltage, so for the 220 kilovoltage DC time constant 220 kilovoltage, frequency fault current 61% is breaker DC breaking capacity, and breaking time 40 millisecond. So by putting 40 and percentage DC time 61, we can solve this equation, and it will provide the total DC time constant 47.7 millisecond. And as we discussed in this page, that time constant TP is L by R, and that L by R we can write this with help of the time constant L by R, we can find out the X by R. So in this formula, if you refer, L by R already we have calculated, that is 47.47 millisecond right now. So 2 into pi means 3.14, and F is frequency. So 2 into pi into F, that is the constant. L by R we already calculated, that is 47 millisecond. We can find out the X by R ratio, and that we can calculate here. X by R is 2 into pi into F into TP, and that will provide the 414.94. I think that we can do the calculations right now. And even doing the calculations, I think this is very small, that we can perform at least. 2 into how much? 3.14, right? Then how much? 50, right? And then how much? Multiplied by 47.57, right? 47.57, right? Now 14936, but this is in milliseconds, so derive into second. So we have to divide by 1000 to comes to calculate into the second. So how much? 14.93 that I am putting here, 14.94. Let me remind you, let me uh, inform you that whenever we perform the ETAP calculations, in the ETAP, this we take as a grid. This we take as a grid. Whenever we do the modeling of the grid, if we do the modeling of the grid, so power grid modeling, rating, in the rating we have to provide the voltage, whatever the voltage we are taking, 11, 22, 33, 400, whatever. And when we go to the short circuit tab, and when we do the modeling of this tab, you can see there is important calculations. What is that? X by R. X by R. That is very important calculations. X by R. I will. So what should be X by R? What X by R we take every time in the E tab, in the power grid modeling, X by R value always I will take 14. If you ask me why 14, what is the backup of this 14 calculations? So this is my backup, 14.94. Okay, so I'm not going to 15 because I'm just 15 also we can take, but generally we take 14. So why we take 14? That is the proof of the 14. X by R. Why X by R? Same X by R here. No, same X by here. X by R we are calculating X by R 14. That I'm going to use. See, this is depend if my frequency is 50 Hz. If my frequency is not 50 Hz, if my frequency is not 50 Hz, in that case, the X by R value will be how much? How much? Let us again perform the calculations. 2 into pi means 3.214 into f is, let us suppose frequency is not 50 Hz, frequency is 60 Hz. So f will be 60. F into how much? 47. Right now how much we have taken? 47.57. So and divide by 1000, right? So 17.92 comes, and we take 17. We take X by R 17. So X by R 14 we take for 50 Hz system. X by R we will take 17 for a 60 Hz system. And this X by R 14 is not again constant. It depends on your breaker opening time, and it's depend on your breaker DC breaking time. And generally X by R 14 and 17 we will take in power grid always. So in the CT sizing calculations, I explained another point also. The power grid modeling, whenever I will do in the ETAP session, I will take X by R always 14. So please refer this discussion for that time. That X by R 14, 14. Every time I will blindly fill 14 here. Hope you are getting the point. Mehul, I don't think that we can calculate that. We can inform to breaker manufacturer that what should be the time. I will try to calculate in the short circuit when we will do the short circuit. Okay, so coming back to the discussion. This XYR already we calculated. XY we calculated. So now XYR is how much? 14.94. I think with help of this we can find out the source resistance. Now, before going to the calculations, let me remind you the power impedance triangle. Let me again remind you the basic of power impedance formula, power system impedance formula. First of all, we should aware about the power impedance triangle. So this is my power impedance X, R and Z, 90 theta, cos theta R by Z, sin theta X by Z, tan theta X by R. R is the resistance in ohm, X is reactance in ohm, Z is impedance in ohm. So Z, what will be Z? Z will be under root of R square plus X square, right? R square plus X square. Yes. So what will be the R? If we do the Z, if we know the Z, R we can find out. R will be Z into cos theta, X will be Z into sin theta, and X will be R into tan theta. because I'm going to apply this formula. So before coming to the calculations, I'm telling you the basic of the formula. Now taking this formula, we can find out the source resistance and reactance. Coming to this now, below is two method of calculations. What we are calculating, basically we have started to find out the source resistance and reactance right now. Hope you remember the source resistance and reactance we are finding out, and for that we are going from this all discussions. So till the substitutions, okay, let us go this later on. Let me first go. So with help of x by r, source x by r, we can find out the source resistance and uh, source reactance value by impedance triangle formula. So let us see this one. Fault level at the point of substation, right? 63 kiloampere. Fault voltage 220 kilovoltage, so I convert into the kV into the voltage. X by r 14.94. I think you are aware about x by r now. 14.94 right now. This is coming from here. Please let me know if I'm, because I need to take this Excel. Okay, so what I'm doing, that I'm taking the small portion of this Excel, and with help of my PPT, I'm doing small calculations. And in the last, when you understood all these things, I will directly go and will put the values here, and it will automatically calculate it. Or we will discuss here then in this Excel, and it will be like you will be aware that how this value is coming. Like here we have all this calculations, so directly we have applied the formula in the Excel. So before coming to the Excel, I'm just have taken and explaining the same. So XYR is 14.94. So now we let us go to the again power triangle formula. We know the x by r. X by r we know. So what we can find out? We can find out the tan theta, right? Right now. Tan theta we can find out with help of x by r, and from the tan theta we can find out the theta value. Am I correct or not? Theta is what? Tan inverse x by r. If like you are down your energy, we can take in the next session, don't worry. Like if you all is down, we can start from the next session.
No, please
No, we
continue.
can continue.
Yeah, so theta is x by r we know. We can find out the theta. So if we know the theta, so we can find out the r is r, and we can find out this x also. Okay, so coming to this here. So theta is tan inverse x by r. So theta tan inverse 14.94. And I think if you facing any difficulty, you can use this here also. I think from the Google also we can do the tan inverse. This I think that also that tan inverse calculator right now. I think we can do. I have not tried, but I think we can do. Or if you have the uh, engineering calculator, you can perform.
Yeah, it's nothing. Inverse of tan
Arc
14.
tan
14.
14.94. I'm
Yeah.
not sure. I'm not writing it. Angle is 86. I think that same is coming here. Let me see. Yeah, same right now. 86.17 right now. 86.18. Correct. So theta is 86.18, right? So theta we know. So we can find out the cos theta. Cos theta. Cos into theta. So cos into 86, right?
Yep.
It will,
Zero
yes,
resistance.
it will give the
Resistance.
this 0.67 sin theta. And it so what we have done basically, this sin theta, this 0.998. So cos theta and sin theta, now we derived from this two. Now we go to the impedance ZS. And what is the ZS? ZS is source impedance. Source impedance, since we know the again this source impedance, this formula we can also follow. Source impedance means we can apply this formula. V is equals to IZ right now. V is equals to IZ. And In case of three-phase system, we can write V is equals to the V is equals to IR. Right now, this is my Ohm law. So I am putting V is equals to IZ. Or for three-phase system, we can write V is equals to 3 into I into Z. And when it comes to the short circuit, so we can write as a V under 3 into I as C into, I think what formula we have followed. Let me recall that. Yeah, that formula. Z source is equals to the source impedance is the source voltage. So what we are doing basically, we are calculating this impedance, and for that we are dividing the voltage divided by current. Voltage divided by current, it will give the impedance. V is equals to IR. We can relate like that. V is equals to IR. I'm just V is equals to IR. So R will be V by I. That we can relate like that. Or we can say in place of R we are putting as the Z, and V is my source voltage, that is we can take 220 kV or 400 kV, what we are taking, divide by root 3, because we are working in three-phase system. So root 3, and in place of I we are putting the short circuit current, so it will give the short circuit impedance ZSC. ZS or source impedance, we can say, or not the short circuit, source impedance. Z source you divide by ISC of the network fault current, right? So based on that we can derive the source impedance, that is voltage divided by fault current into root 3, and 2.017 is my source impedance value. So now we know the source impedance ZS, we know the cos theta, so we can find the resistance and we can find the reactance, right, by applying this formula. R is equals to Z cos theta and X is equals to Z sin theta. So Z we know, cos theta we know. So R is equals to source impedance into cos theta. So 2.07 into cos theta, 0.13 ohm source resistance, and source reactance as ZS into sin theta. So that is ZS 2.07 into sin theta, 0.978, and X coming 2.013. This is one approach of the calculations. Or if we do not wanted to go in such a big formula, directly we can go like that also. This one second approach. Z, we directly calculate the Z is equals to U divided by root 3 into ISC, right? And that will come 2.06 or 2.07 as we have seen here, same value, right now. So if we know the Z, right, so no need to calculate the cos theta and sin theta. We can directly find out the R and X. But why? Z square is equal to what? R square plus X square, right? As we have seen here now. Z is equals to under root R square plus X square. So Z will be R square plus X square. So what I can do, I can take R as a common. So Z equals to R under root 1 plus X by R square, right? So R, what will be the R? R will be Z divided by all this. So Z already we know 2.016 divided by under root 1 plus X by R. X by R is 14.94, that already we calculated. So from that we can find out the R source, that is 0.135 ohm. So when we know the R, when we know the Z, so X will be under root Z square minus R square, right? So that also we can find out. And I perform the calculation by both the method and I compare the result. So this is coming very much close. 2.07, this is same 2.0135 and 0.135, 2.0134 and 2.012. That is a small difference. So both we can apply, right? This is till now we calculated the source resistance and source reactance value only, right? What I need to do, I need to calculate the uh, fault current. In through fault current, we have seen that through fault current, uh, it will be decided by the total resistance, total reactance value, total resistance, total source resistance plus line resistance, total reactance, total source reactance plus line reactance. So we know the source resistance and source reactance, that already we calculated. Now we have to go to the transmission line resistance and reactance value. So should we continue the session, because I think already 2 hours we have completed. So are you like able to like ready, or should we continue the remaining session in the next weekend? Like based on, if you saturated, then we can go to the next. I'm not in the hurry. Basically you should understand the concept properly. Okay, so can anyone summarize the session so far what we discussed? So for the next weekend, your homework, I could not review the last weekend homework, that I will review after the city session. So let me complete first the city calculations. After that I will review the last week session home assignment. And for this week the home assignment uh, uh, is to decide the city core, city number of core for entire grid. And you, if you are doing mistake, that is fine, we will discuss and we will correct this, but at least you attempt this, and it will give the overall of the city core selection. Okay. Okay, so we'll close for today. I hope that you learn something. One point we learn, very very important point: every time I am going to use xyr here, or anyone, any, not me only, any eTap engineer, when they work in eTap, every time in the Power Grid they use xyr14, they will write, or you should write if you are doing the modeling. So what is the background of xyr14 that we discussed today? Okay, that is the point one. And we discuss what other we discussed. So we discussed about the nature of fault current, that we discussed. Then we discussed about the city requirement, the relay models, that type of protections. I think these all things we discussed. Yeah. Yes, I think that is important. Yeah, because CTVT sizing is one of the skill, one of the important tasks that need to do. Okay, thanks, Alkesh. Thanks to everyone. So we close today, and from the next session, I will directly come. I will directly come on the transmission line resistance. I will not go on the source resistance now. Okay, I will come directly on the transmission line resistance. So
Sir, one question, sir.
this much is
Sorry.
yeah. 1 second. So from the next, I will discuss transmission line data, and for that I will start discussion. Yeah.
In case of small capacity generator station, maybe for example 5 MVA or 10 MVA, but the voltage level is 33. So should we consider 33 kV of fault level, or just a small substation, maybe the 10 MVA fault level? What fault level we should consider in that case? Should we go with the voltage level KA as per CA, or the actual substation capacity, generator station capacity?
No, as per CA, where we are going as per the voltage, you can see, na.
No, no.
Okay,
This, for example, this, yeah,
now you are telling if this is not the
yeah,
this substations, this is generator, right? Now,
generator station, yeah, yeah.
in
In that case, yeah,
yeah, in that case, I think we have to do the overall modeling, and we can find out the fault current for that generator.
okay,
This is the approach number one, Salis. And secondly, I think we have some CEA in that also. I'm not confident that whether we have CA for that also or not, but yeah, we can go with the actual fault current calculations from the ETAP we can calculate, and that fault current we can consider in that.
okay,
But give me some time, and I will discuss this, and then I'll again confirm you.
okay, okay. Thank you.
Yes.
Sir,
Yes, you.
I think for this type of calculation, we also go for the fault MVA. I mean, we calculate the from the percentage impedance. We go for the we find out the short circuit test. I mean, short circuit current with the impedance of the generator. Is it not?
Uh, okay, so you are telling that we can.
We divide the MVA with the percentage
Actually, what will
impedance, and
happen?
then we get.
What will happen? What will happen when it comes to the generator generating substations? So there is a generator site, like what we can say. we have the generator, and after that we have the generator circuit breaker, GCB we say, and we have the CTVT also. And then it goes to the GSUT, then it goes to the generator step up transformer, and from that we step up the voltage, and then we feed to the transmission line. So if we are working till this location, or we are working on that locations, so in that locations we can directly take the fault level as per the voltage, because there will be back feeding also, and that will come from the grid, right, Sivam? uh,
Yes.
that will come because when we do the synchronizations we take the reverse supply from the
Mm-hmm.
grid, and for the synchronization, so that we can take the fault level as per the grid, fault level as per the voltage. And when it comes to this locations, so that two fault current, as you are telling, that we can calculate the fault current based on the percentage impedance. Right now your point is that,
Yes.
and we can find
Yeah, I was talking about the
the
session.
fault current coming here, and that we can say the through fault current, that is the one point. Or we can take that this generator, how much they are like contributing the fault current based on their transient, the XDC value. So it will also contribute the fault current. So which one is higher, that higher one we can take. So for this, I'm sure we can take the fault level. When it comes to this locations, there is two approach. We can find out the short circuit contribution by the generator, and that we can take. Or this throw fault we can do, and we can see that which one is the higher fault current, and the higher fault current value we can consider. But I'm not telling the right now the correct answer, because I have also need to check, because without checking, please allow me. I will check this. Okay, this region. This for this Salis, you can go with the grid fault level. Okay, I'm not like I have not done this portion currently. Need to recall. Or anyone have any things they can add down?
Yeah, Ajit.
So, sorry, say the question again. Apologies, I was just away. Say the question again, or is it too late for you guys?
This question.
Mhm. Yeah.
They are telling that when we are doing the city sizing, so how to find out the short circuit, which short circuit current we have to take, like what we are doing, the IK max value. The IK max
Mhm.
value 63 kiloampere we are taking, and that we are taking from the CEA, that for kilovolt is 63 kiloampere. So that voltage we are directly taking here, 63 kiloampere. But when it
Yeah.
comes to the generator, so generator, so that we have drawn like that. So the
Yeah.
generator side, the fault current we should take as per the CEA, or the fault current we should calculate as per this the generator. That was the questions, right, Salis? Are you there?
Yes. Yes. Yes.
Yes, Ajit, you have one doubt.
Basically, the thing is like from my experience, you calculate the generator, because the generators, you are taking 63 kA, right, which is from CA, but the generator itself, it depends on how much it contributes. If you have one generator or two generator or three generator, we usually use personally use whatever the available fault current from the generator. Based on that, or whichever is the maximum, just compare it and then use this one.
Okay, Kamesh. Okay. So I think that point, Salis, you can also consider.
Yeah,
That's fine.
one doubt.
Yes.
I
Yeah,
have a
one doubt. So continue.
Yeah, Ganesh.
yeah.
Yeah,
So
actually,
For suppose we consider wind farm from this side. For suppose wind farm means for suppose they will consider about feeder wise
Yeah, feeder
for
wise.
this part.
Yes, feeder wise, Ganesh, feeder wise.
yeah. Okay, that is nice. I think they will calculate for suppose feeder that is for suppose 25 megawatt per feeder, 10 megawatt. So they will consider the 10 megawatt of power. They will consider for that short circuit losses, right?
Yes, right, Ganesh.
Yeah, okay. Thank you.
Yes. So Ganesh, in your case, I am confident, so I am telling this is right. We take feeder wise.
Yeah. That's it. Actually, yeah. You are telling that like generation one, but in the data form, every individual generating is actually like 1.5
Yes, correct.
2 megawatt.
Generally,
They will
10 megawatt
every
or 25 megawatt is one generator, wind
yeah one.
generator.
I think in that scenario we'll consider the 25 megawatt like feeder. We will consider as a generator total amount, right?
Right, Ganesh.
Yes. Okay. Thank you.
Okay. Yes.
Um,
I
on the
have a
basics,
question. Raghav, I have a
Yes, Ganesh.
question.
Yes, I can hear you.
Sorry, I have a question which is at this moment not related to this topic, and I'm just wondering whether anybody in the class has ever come across it, which is earth loop impedance. I think I spoke to you regarding this. Has anybody calculated earth loop impedance? If not, then it's fine. I'm just asking if anybody can help me out, or earth loop. I do have a standard, and I know IEEE wiring standard, but I just wanted to know whether has anybody ever calculated the earth loop impedance, basically.
Yeah, if anyone have done, they can share their experience with Ganesh. Or if any
Yeah. But now it's too late for you guys, and
yes. So,
I
so
don't
what
want
the
to.
time in UK at present? Morning?
It's 6 o'clock in the evening, so
6. Oh,
it's
that
fine.
you are good time.
The problem, yeah, at this moment. But when we start, it's a problem for me. And anyway, I just want you to leave you guys for now. You guys have a nice evening, and have a good night, guys.
Okay.
Hello, Kamesh.
Yes.
Were you asking about LV side?
Yeah, on the LV side. This is let me
Okay,
tell you,
okay.
coming on the LV side. Who's
Okay,
this?
I have done that, and I'll talk with you regarding that. Okay, I'll discuss that with you.
Can we talk tomorrow?
Okay, Kamesh, I'll let you know that very
Sorry,
soon.
your name. I did not get your name. I did not get.
My name is Sanket.
Sanket. Yeah.
Yes, I will let you know the timing soon, and
Yeah.
we can discuss that. Okay.
Need to submit this one tomorrow. That's why I was a little bit. It's a
Okay,
bit
then we'll
dragged.
talk about that tomorrow.
Yeah, sure.
Okay.
How
What time will be convenient for you?
my time? Oh, you can whenever you wake up and you call me. I will I will answer, because I need to submit this one. This has been dragging on for a long time, and basically, yeah, I have to submit this one. So I just wanted to discuss with you. So you got my number in the WhatsApp, anyways.
Okay. Okay, I'll see you tomorrow then.
Sure. Just ping me. I mean, I'm based in UK, so something around 5:30 in the morning, because I go to work at 7:30 or something. So your time will be 11 o'clock. If you are working from home, I do not know. Or I mean, I'm just asking you. Whenever it is suitable for you, then answer, Sanket. Yeah.
Okay, Kamesh, I'll message you accordingly then.
Thank you. Thanks very
Thank you
much.
so much. Thank you so much.
Yeah, bye.
Bye.
Bye, guys.
Yes. Bye.
Okay, sir. Have a nice time, and thank you so much for the session.
Yes. Okay. Sanket. Thanks, Kamesh. So we are closing now. And good night, and thanks for
Yeah.
time.
Good night. Yeah. Bye, everyone. Good night.
Bye.
I see you.
Bye. Good night.